Hi, thanks for watching this presentation on interseismic strain for the southeastern Tibet from Sentinel-1 LiCSAR and GNSS data. The ongoing collision of the Indian plate with Eurasia has created the Tibetan Plateau, which is the largest deforming region on the planet, with widespread earthquakes and active faults. Deformation in Tibet has been the focus for heated debate over the last decades. Much effort has been devoted to quantifying slip rates and locking depth of major faults in Tibet, either geologically or geodetically. The left lateral Xianshuihe fault lies at the eastern edge of the Tibetan Plateau. Crust to the west of the fault rotates clockwise around the eastern Himalayan syntaxis. The Xianshuihe fault is tectonically active and is considered to have substantial earthquake potential. Creeping behavior has been reported along some sections of the fault. However, the spatial temporal details of creep are not well characterized. In this study, we obtain a high-resolution velocity field for the Xianshuihe fault region from LiCSAR LiCSPAS processing chain. We first make interferogram using LiCSAR system. In some cases, gaps exist in networks due to no acquisitions, severe decorrelation, and/or unclosed loop phases. We fill these gaps by creating or repairing specific interferograms so that networks are well connected. This is a typical small baseline network of interferograms. Before time series analysis, incorrectly unwrapped data are identified by checking the coherence and coverage of unwrapped data and loop closure, and these are removed. Bottom panel shows the final network used for time series inversion. In LiCSPAS processing procedure, there are 5 steps for data preparation and 6 steps for time series processing. We first downsample the data by a factor of 10 to a pixel size of 1 km. Gap cost data are used for tropospheric correction. After time series inversion, we generate a mask to differentiate between good and bad pixels using several noise indices. The pixel is masked if any of the values of the noise indices for a pixel is worse than a specified threshold. After LiCSAR LiCSPAS processing, each frame has its own independent reference area for velocity determination. Then, the inside line-of-sight rays are transformed into a Eurasia-fixed reference frame by using GNSS velocities. We combine INSA observations with published GNSS data to invert for a velocity and strain rate field for the region using the VelMap approach. Before VelMap inversion, we multi-look the inside line-of-sight data to a spacing of 3 km. We create a triangular mesh with vertices at 10 km spacing. This is the inverted inside line-of-sight velocities in GNSS reference frame. We draw a profile across the Xianshuihe fault. We can see a sharp velocity contrast there, particularly for the descending velocity field. This indicates the fault is creeping at the surface with a shallow locking depth. From the stream rate field, we can see the stream accumulation along the major faults in the region. We know that high stream concentrations along the faults, particularly along the creeping segment, although noting that VelMap will smooth out the stream. Then we calculate the full 3D velocity field. Note that viewing geometries are relatively insensitive to north-south motion, so we use the interpolated smooth north-south component of the GNSS velocity field, assuming the north-south motion from GNSS is correct. The inside velocities agree with the GNSS measurements. The east velocity map shows a pattern that generally follows what we would expect from left lateral motion of the Xianshuihe fault, with sharp velocity changes across the fault. Thank you very much.